Okay, so this is lecture 21 in section 4. We will cover support vector machine, nonlinear with kernel trick. And also we will talk about how do you use SVM in practice. So this is the module 1 of the kernelized SVM.
And we already covered history, large margin definition, and margin definition, and the optimization formulation. So today, what I'm going to cover actually is the last two sections in this whole different elements of SVM. SVM is extremely complicated and mathematical derived model. So I split it into 3 different sections. So this is the nutshell of SVM. When last time we covered half of the basic optimization formulation, but not exactly this formulation on here. Today I'm going to, actually next time I will cover how do the C got introduced in this optimization formulation. So today it's really about representation. So how do you represent samples? So the most important idea behind SVM is called kernel trick. And that kernel trick is the definition actually just a inner product. It's really, so instead of thinking about each sample represented by features, now I'm thinking about similarities among 2 samples. The majority, the most important features, the most important pattern make use in the SVM is not raw features, it's pairwise similarities among samples. And how do you produce it? It's produced by something called kernel trick. So for example, in this case, kernel behind sample X and sample Z is its phi X, which we learned before, its basis expansion of the feature. Inner product is the phi Z, which is the basic expansion of the point Z. So this still sounds pretty hard and abstract, and we're going to introduce why this is. I see, so there's actually a small mistake here. So the curve, I'm going to fix it. Should supposed to be X and Z. So, but it can be Xi and Xj, and then you replace Xi and Xj here. So most important is we're using pairwise similarities as the major features, major important pattern to use for classification. So last time we talked about classifying using linearly separable SVM, and then so the linearly separable SVM, it's really simple, right? So for example, you're given the training data, like in this case, so you have only one X, only just one X, which is a number line. The colors represent the different 2 different groups, 2 different classes. And really easy, what you're looking for is the separation margin, left and right, which we call X minus, X0, and X plus, right? This is how we defined in the last class. Then the margin, the distance among X plus and X minus is the margin, that M margin equals to actual 2 over W. And that's what we proved, W transpose W. So maximize margin equivalent to minimize W. Then subject to, you classify all the samples correctly. So this side is -1, this side is +1, -1, +1, and then subject to, if you still remember, for all these points in the training data, I want to have my yi, which is the true label, times the xi or maybe W transpose I, it's the same thing, W transpose xi class B larger or equivalent to 1. So this whole thing is the formulation, whole thing is the scoring function to train W, to look for the W and the B best fit my training data, which is represented by the point here. So this is what we covered last time, right? So this sounds really nice. However, when you have square root, yes, you're right. Actually, yes, this has a square root here. Yes, thank you. Yeah. So this sounds nice, right? But however, when you look at the data, just there's a little bit error or some kind of noise. Like this red point is on the right of the two blue points, and there's no way you use a linear separation to separate the 2 points here. So what can you do? Very easy. So same trick as we did before. Regression goes to polynomial regression, and you just add a new feature space. You convert your x space into phi x. So our old is x, right? It has olding feature x. Now I'm just converted it into phi x, including both x and x squared. And in this space, you actually can you can totally just use a linear separation line to separate the two classes. And this is exactly the trick. So in this case, this is called sec. Don't worry about this red point I just added there. So now we moved from the left case called the linearly separable case into this is called non-linearly separable case. We can totally separate two classes using actually it's equivalent to a nonlinear line in the original space, but actually it's a linear line in the phi x space. So this is almost the same trick we had before. Extend linear regression into polynomial regression just by extend x into phi x. So even more complicated, but actually there are a lot of data looking like this. So you might have some kind of one class quite densely together, and then the other class all like distributed almost all over the space. And how would you separate this? So there's no way in the original space, x1, x2 space, you separate the two classes, the red versus the blue, using a linear separable hyperplane, right? We actually define hyperplane. However, if you just extend the x into phi x, then you actually can separate the two different classes, red versus the blue, just by adding one more feature is the x1 times x2, and then also use x1 quadratic, x2 quadratic as the representation. Then you can find a linear hyperplane to totally separate the two cases, the two classes. Okay, question about this.
How did you find that equation?
Good question. So in the end, what do you even know phi x, right? Which phi x? It's coming in the future slides. All right, so just to summarize, when you're given a feature mapping phi, we define the kernel K as KXZ, which is equivalent to phi x transposition phi z. And then we actually in the kernel SVM, and I do not need specifically no phi. The only thing I need to define is actually K. Instead of defining the phi, what I need to define is K. So this sounds still pretty hard to understand, but you will be getting clear in the future. So for this one, it's very simple. you can, so this is one type of kernel, it's 2x1, x2, x1 quadratic, x2 quadratic. This is the first type phi1, right? This is more like a polynomial kernel. And you can also use, this is called Gaussian or RBF kernel. And to do the separation of this type of middle is dense and the other class is almost surrounding to separate the two. So the whole idea is I'm looking for nonlinear separability. I'm using a kernel mapping phi, and then in that kernel mapped space is linearly separable. And it's equivalent to I'm learning a nonlinear boundary function in the original X space. So this remarks is a little bit elementary device. So the whole thing is when we see that we use the kernel trick, it's very important for SVM is when we see that we use the kernel trick to compare the cost function using the kernel. So don't worry, we're going to talk about later to compute. We mean we actually do not need to know the explicit mapping phi. What we really need to have is just this function. So like this function, I don't know what phi, but it's equivalent to phi x transpose phi d for a specific phi. Maybe phi I, let me just try this, phi 2. And the previous design is phi 1, right? So in this design, I have this specific phi, but that's just, I know. But in fact, when you use in SVM, you don't need to know phi. You just need to know what to define the k. So it will go getting very clear in the later slides. So okay, all right. So a little bit theorem. So why do I want to map to the higher dimensional space? If let's look at the when there are 3 points in your training data. When you have 3 points in your training data, you can separate it in R2 space. You can always separate 2 training points or 3 training points with whatever classification combination, a 2-class combination it has. You can always use a linear line to separate the 2 cases. Question about this, because this is the key. It's the fundamental idea of SVM. So, for example, this is the first combination. 1 is white, 2 are yellow. You can always find a separation line, right? And the other case is a 2 white, 1 red. This is the case 3 white. This is the case 3 red. And then this is the other case also. It's this dimension. So whatever combination for the 3 points in terms of their labels provided by training data, you can always separate it, linearly separate it into 2 classes. Question about this? And this is just called linearly separable case. We can always linearly separate them into 2 classes when you have 3 training points. All right, then we extend it. When you have endpoints, in general, you can always linearly separate them into 2 classes in the n-1 space. So in the end, it just shows me if I can project my feature x into a phi x, if I have n data, I can project it into n-1 or even larger larger than n-1 space. Then in that phi x space, I can always linearly separate the 2 classes. if it's larger or equivalent than n-1, it's guaranteed I can find a linear separable hyperplane given the n training data. That's the reason why we like to project it into higher dimensional space, because we can always separate them into two classes no matter what are this original permutation of the class labels for that endpoint. Sure.
Aren't we increasing the complexity of the model?
Great question. So if you go to the phi-x, then what's the computational cost? That's exactly the question we're going to answer. And why? That's the reason why the kernel trick. All right. So we go to x to phi-x and already had it. So there's a reason why you do x to phi-x, because you want to project into higher dimensional space, make your training data to be able to be separated, linearly separated. +1 class and -1 class. All right.
Great. So this is the end of this module. See you in next module.